Now, I would like to say a couple of words here about our presenter. First off, Dr. Tiwari, thank you so much for joining us. So I have known you since childhood, and I have never forgotten all of the fun times we've had as siblings. To me, you will always be my big brother and my favorite cousin. I am proud of the many accomplishments that you have achieved in your life, and I'm looking forward to seeing many more. Additionally, I would like to thank you for coming out to our college today to present your research to our college community. It will give our engineering students something to look forward to in their coming future, especially if they see a role model such as yourself, who is in the same exact profession as them and who was always determined to never give up despite any challenges and obstacles that were thrown your way. Now let's hand it off to Dr. Sidhant Tiwari. Thank you.
All right, just let me share my slide screen. I'd like to start off by thanking you for the introduction. It was actually quite nice to hear. My favorite part was that this is being recorded and I now have proof that I'm your favorite cousin. Just want to confirm, can everyone see my presentation screen?
Yes, but we cannot see your face.
Oh, okay, my bad. Oh, where does Zoom thing go? All right, am I there?
Yes.
Okay, perfect. Let me just pull up that. Okay, so again, thank you all for coming to the talk. As you well now know, my name is Sidhant Tiwari. I am a recent, I guess not recent. I graduated my PhD back in 2020 at UCLA. And today I'd like to go over kind of some things I wish I knew before I started my PhD. Some things I just think would be helpful for you to know if you're thinking about applying to one. And of course, covering just kind of a broad overview of my research field and my research. The one thing I want to say at the very beginning is that this is all my personal perspective. And you shouldn't really ever just take one person's perspective when making any decisions. No one's background is going to completely match yours, so make sure you get like several people's opinions and all that stuff and try to figure out what interests you and what is a good fit for you personally based off all that. And so first, I'll be talking about some important things that to know that will influence your like day-to-day life as a PhD student and some advice I have to those who are considering it. Then I'll probably go, oh, it's not probably, then I'll be going into some background on MEMS research, which is my research area. And finally, I'll go into the specifics of my PhD research, which is a subset of MEMS called multiferroic MEMS, where I'll go over what are multiferroics, what are some applications, and then a few experiments we actually ran during my PhD. And with that, let's begin. So first, a little about me. I'm a local kid. I grew up in Riverside, California. Went to La Sierra High School, where I graduated back in 2009. So I am a number of years older than all of you. My parents are Indian immigrants and both of them worked retail jobs. So I'm the first in my household to actually go to college. I went to UC Berkeley where I majored in engineering physics, which is just what they call applied physics for some reason. And I graduated back in 2013. I then went to UCLA for graduate school where I got my PhD in electrical engineering early 2020. During my PhD, I worked in Professor Robert Candler's lab, where I did research on RF multiferroic MEMS. And so just to kind of elaborate what that means, RF just stands for radio frequency. Um, and it's a like, really wide range of electronics applications, Wi-Fi, cell phones, microwave ovens, wireless chargers. These are all examples of RF technologies. Multiferroics I'll discuss more in depth later, but they're essentially devices where like magnetic properties and electrical properties of the materials are like combined. And finally, MEMS, this stands for micro-electromechanical systems. And they are a very broad class of small scale electronics, and they include things like miniature motion sensors, microphones, and clocks. Since graduating last year, I've been working as a postdoctoral researcher at UCLA, half-time for Professor Candler, and then half-time for Professor Carmen, who runs the TAM Center at UCLA, which is a research center dedicated entirely on the research of multiferroic devices. And so far, my favorite way to kind of describe what a PhD is and like the journey of getting one is this illustrated guide by Matt Might of University of Utah. So first, imagine a circle that contains all of human knowledge. When you finish elementary school, you know a little. By the time you finish high school, you know a bit more. When you get a bachelor's degree, you gain a specialty, but you gain a breadth of knowledge and then a little more of a specialty. Master's degree will deepen the specialty. And then once you begin your PhD process, you'll be reading a lot of research papers, talking to people at the top of their field, and that'll kind of take you to the end, like the edge of human knowledge in your specialty. And so now you're at the boundary, and then that's just where you work for a while. And for a couple years, you're just pushing at that boundary till one day you actually add something and the boundary pushes farther. And that little dent is your PhD. And so you've now advanced knowledge in this field you've been studying for years now. And so everything just looks different. But this last bit of the illustrated guide, I think, is really important because there's this saying my boss likes to say, where if your only tool is a hammer, every problem looks like a nail. And so when you finish your PhD, you are the expert on your work. But if you look at this, there's still a lot more knowledge out there. And so it's really important to keep yourself surrounded with people with a very diverse knowledge base. If you only surround yourself with people from your field, everyone's ideas to tackle the problems are always be the same. And so collaborating with people outside your field will help you come up with new ideas, learn more, and just keep pushing boundaries. And so the major difference between a PhD as opposed to a bachelor's or a master's is that a PhD is actually predominantly research, not coursework. When I was pursuing my PhD, I would often get questions like, oh, like, how many classes are you taking and all that stuff. And honestly, after my master's, I had a total of, I think, what was it, 4 classes I had to take. And at UCLA's quarter system, so that's not a whole lot. Pursuing a PhD, or at least a PhD in engineering, which is my background, is more like a job than going to school. What you'll do is you'll attach yourself to an advisor, and that advisor will have a research lab that you'll work in. And the PhD students are usually hired to be part of the research lab part-time. So you'll be 50% a student and 50% working part-time. Or if there's enough funding, because research costs money. If there's not, that's usually when you start teaching or stuff like that. In my experience, yeah, it's the norm to be about half your time doing research and then half your time teaching and all that. And when I say half the time doing research, is because you're still a student. So half those research hours is your education. And then you have another half of like employed hours, either teaching or doing research. The biggest thing I think that matters when picking a PhD lab is the advisor himself or theirself. The advisor will kind of determine the lab culture, and that's what's going to determine whether or not you're going to enjoy working there. because a PhD is a lot like a job, and everyone knows that at your job, your boss kind of makes or breaks whether or not it's a good job. And then another major factor in what dictates the research and what you'll be doing is the facilities in your university and in your advisor's lab. If you want to do research on kind of material deposition technology, your advisor needs access to tools for material deposition. And tooling is expensive. So basically, if an advisor has equipment, they will be that will kind of dictate their future research trajectory. And here are some things that I think are important to keep in mind and to ask people about, ask an advisor about, or ask this, better yet, ask the students already working for the advisor if you're contemplating joining a lab. How would people describe the advisor's management style? This varies a lot. My advisors have always been very hands-off, which works well for me because this just what works best for me. I'm kind of self-motivated. I like to learn on my own. Basically, I just check in with my advisors once a week, and they make sure that I'm not running into anything like running into big problems, and I'm staying the course of the work. Some people don't like that. Some people like a lot more guidance, in which case, for my advisors, that would not be a good fit at all. But then there are plenty of advisors that do offer a lot more guidance. So that's a good thing to keep in mind. Where does the advisor see their lab in 5 years? So that's a good thing to keep in mind, because a PhD is a multi-year commitment. If you're interested in doing research in something the advisor is doing the day you start, but the advisor's I don't see myself continuing that project or continuing pursuing that because it just doesn't fit his long-term goals, well, then maybe that's not the right lab for you. Maybe a different lab would be a better fit. And then there's also the do this students have to TA often? That could be a deal breaker if you particularly don't like teaching. What determines if a student has to TA is actually usually the funding in the lab. And you'll see a lot of the points here. And then just most things about your PhD will be determined by funding, because everything costs money to do. And so they have to pay, if you're hired to work in the lab as part of in addition to your student time doing the research, that usually covers your tuition and stuff like that. But then naturally that money has to come from somewhere. And so if they don't have funding, you often TA. So that might be something that you want to know about. Do you have to TA often? In my experience, usually people TA 1 or 2 quarters at least. It's not too often, considering, but again, that's just my personal experience. How long do students typically take to graduate? That's a big one. Some labs I've seen, because what that goes to point 6. What determines really what you graduate a PhD is that there are these department requirements, but your advisor at the end of the day signs that paperwork saying you're ready. And so what is the advisor's requirements to be ready, and how long does it take for the students to hit those requirements? Some labs take longer, some take shorter. Maybe you want a shorter one just because you want a PhD and get out. Maybe you want a longer one because you actually want it gives you more opportunity to get a lot of more research done, and you have other research goals down the road, something like that. Well, I missed one. Do students take internships? A lot of professors have varying feelings on internships. On the one hand, it means that they don't have to pay for you because you're working somewhere else for a while, and that kind of frees up some cash. On the other hand, if you're not working for them, that work is not getting done. And so if there are deadlines, you just might not be able to, it just might be really frowned upon. Might not even be allowed to take internships because somebody has to get the work, because these projects, these grants all have deadlines. Where do lab alumni go to work? This ties into number 8. What skill sets do students learn working at the lab? You typically won't get, your career after graduating typically won't be what you do your PhD research in, especially if you're not going into academia, if you're going into industry, because your PhD research will be kind of at the forefront of like kind of at the forefront of knowledge, but industry is more, since they're trying to work on products and they're all worried about pricing, costs, all that stuff, they tend to not be as risky, but what tends to transfer are the skill sets you learn. And so people in my lab, we kind of get a lot, we work a lot with sensors, we do a lot of like manufacturing and stuff like that. So we've had students go on to companies where they're designing like sensor systems, actuator systems, stuff like that. Not stuff that they did during their PhD, but the skill set is the same. We've had students go on to other companies and work for as part of their manufacturing engineering. And so like, you know, we don't have necessarily degrees in manufacturing, but we've gained a lot of experience in manufacturing processes because of our PhDs. Now, how often do students publish their work or present at conferences? This is really important if you're interested in academia, like a scientist position, or even becoming a professor down the line, because publishing your work and presenting it at conferences is what makes you visible. It's what makes people know that you're actually doing research. And if you can't provide proof that you're doing research and that you actually have a background in the field, it makes it a lot more difficult to get like these academic positions, because the whole reason these academic positions usually exist is because these places want to publish, present their work. And so you should have a track record of doing that. Is the work more computational or experimental? Again, this is kind of specific to engineering. My work was very experimental. We're building, we're doing like some design work, and then we're spend most of our time building things and testing them. A lot of people I work with, they would do a lot of computational stuff, developing new physics models for materials that we just don't have any experience with, or special custom physics models where it's kind of worth their PhD just to like make the model, because there's currently no commercial software even capable of handling these problems. Because again, we're at the forefront of knowledge, and so you're often tackling problems where there just are no tools to work with. And so people can spend their entire PhDs just doing computational work. Is the work often collaborative? This is good if you're interested in a lot of interdisciplinary work. If you're interested in networking, this is also very good because you meet more people that way. If you collaborate, you often meet a lot more professors also. So it's not just other graduate students, but a lot more professors, which means that you will, again, have more people that you can use to pull contacts for later, or to provide letters of recommendation. If you're interested in like a scientist job, so we'll often ask for letters of recommendation. Does the advisor have tenure? So if an advisor has tenure, what that means is basically more or less they cannot be fired unless they do something like really egregious. It's kind of a safety net for, once you've established yourself as a professor, you've proven that you can run a lab. If you have a string of bad ideas and like nobody publishes and like it just isn't going well, you aren't bringing in grant dollars, it kind of protects you from being fired. So if you ever are in a slump, you're safe. As a result, though, different advisors kind of handle tenure differently. Some of them will, if they do have tenure, will become a lot more relaxed. But then as a result, though, that means that you might not get as much attention as you want. So that's something that us as students and to keep in mind. Some advisors I've seen, once they get tenure, they actually some of them actually get more focused on their research, because they're no longer worried about hitting all these milestones required to get tenure. They could just focus on their research and nothing else. And if an advisor doesn't have tenure, usually that means that they're working to get it. They're younger faculty. That means it'll probably be more work for you, but it'll be a lot more hands-on mentoring, a lot more hands-on guidance. And so if that's something that might be interesting for you, that's something to keep in mind. And then there's, oddly enough, like people like my advisor, where when I came in, he didn't have tenure and he got it like a couple years into my PhD. And honestly, there wasn't really much of a difference for him. So, it's something to ask the students there. Where does the advisor usually get their funding from? And again, point 14, which is the most important point. Does the advisor have funding for you? there's one thing I didn't really understand before I started my PhD is the importance of funding, because you don't really think about it as a student, but basically like all the labs you see on campus and all the things that professors are doing, they all cost money to run. And if the advisor doesn't have funding for you, yeah, you could work for them, but you know, you need to pay your tuition or something somehow. If they have funding for you, you can now, actually, if they don't even have funding for you, you might not be able to work for them, because the work you need to do, like you need to buy materials, you need to pay contractors to make stuff for you. Even just licensing software to do simulations will cost money. And so that kind of leads to my next point, where most of your PhD research will be determined on what your advisor has money to work on. You can't really work on anything. Well, you can work on anything as long as you can convince someone to pay you to do it. Most of an advisor's job is actually just applying for research grants to keep the lab going, to keep the students able to work there, to buy materials for the lab, all that kind of stuff. And if there's not enough funding for you, you can't be hired part-time, which means, you know, you need to pay your tuition, so you need to be hired somewhere else. I don't know if I mentioned this before, but typically if you're hired part-time, again, it depends on how many hours per week you're hired, but at least at UCLA, actually, I'm not going to throw out the number because I forget what the percentage is, but basically if you're hired a certain amount of part-time, UCLA will cover your tuition and stuff for you. Well, your advisor will. And so in my experience, most PhD students don't really pay for their PhD once they join a lab. If the advisor ever runs short on funds and then they can't pay to hire, like they can't afford to hire them, the advisor, again, in my personal experience, will help the student get a TA position or a reader position to kind of help them get the funding to pay their tuition and all that. But again, that's just my personal experience. There are a lot of different kinds of advisors out there. I would not be surprised if there are a few that have students pay their tuition more often than what I've seen. And so most research funding, again, that I've seen have come from government agencies. I have a few logos of just a small sampling of ones I've pulled up here. DARPA, the National Science Foundation, NSF, CDC, that's been in the news a lot lately. EPA, pretty much every government agency I have heard of has had some branch dedicated to funding research. For engineering, I have found that a good chunk of them good chunk of engineering grants end up coming from different military agencies. For instance, there's DARPA. DARPA is a DoD-based, Department of Defense-based research funding agency, specifically just focusing on funding research, with the goal of kind of seeing what the limits are of the current US status of the technology. I have had a professor explain it to me as DARPA has about 80% of their projects fail. And that's what they want, because they want to know what the edge is as to what is currently capable. And then there are two other agencies that are similar, ARPA-E, which is the same thing, similar to DARPA, but for energy, IARPA, which is similar to DARPA, but for national intelligence. There's NIH, which does a lot of medical funding. NSF is pretty broad in their funding view. Each agency will have kind of their own goals in mind, and they'll kind of determine what they fund and how much money they give. NSF has really has a really broad view, and typically don't require as much work for the grants, or as much feedback on their side, but then conversely, the grants tend to be smaller. DARPA tends to give a lot more money, but then DARPA, what they will do is they will divide their projects into 2 or 3 phases, and basically you have to report monthly or quarterly, and as long as they like what you're reporting, you'll continue getting the money. But then if they decide to knock you off the phase, then you well, then the money stops. And so it's a lot more money, but it's also a lot more work. And so there's trade-offs there. And professors tend to have kind of favorite agencies because, you know, whether it's their pitching style, their writing style, or just like their area of interest, it often seems to align to like one or two specific agencies. Like for instance, my boss does a lot of work with NSF and DARPA, a few other military funding wings. One thing to know though is since funding is so important, students can actually get their own funding, but it's usually for a lot less and is a lot harder to get. Not just students, prospective students too. So some agencies like NSF, when you're applying to graduate school and you're in that window, I think early PhD or senior year of your undergrad, you can actually apply to these NSF grants. And if you can win one, that actually gives you a lot more freedom because now you are suddenly a lot less expensive to join a lab because you can pay part of your own tuition, part of your own salary, and just gives you a lot more freedom. And then when you are a PhD student, you could also apply. There are several also. I've noticed several companies have them. In fact, I had one through Qualcomm for a bit, which is kind of an RF technology, kind of mobile electronics company. And so that's just something important to know. If when you're applying, I have heard that some students will get rejected from schools, but then they manage to win like an NSF fellowship. And so suddenly they're cheap. And since the PhD application is a lot since PhD is like a job, a PhD application is like a job application. And so if you're suddenly cheaper and you let like a professor you're interested in working for know that you have this fellowship and they're interested in picking you up, that I have heard, like, I haven't experienced, but I've heard that can reverse some acceptance decisions. So you're now accepted to that school. And so if you're preparing for a PhD, I think the most important thing to do is to kind of inform your decision about what you're going to pursue it in. Most things you do to inform that decision will benefit the application. For one, applying to internships to get hands-on experience. I have my PhD background in MEMS. I was not planning on doing MEMS until literally the summer before I applied to graduate school because I had an internship for another electronic, like it's still microelectronics, but a different field. And it was honestly like the research or the field just didn't really interest me all that much once I got my hands-on experience with it, but I wanted to do something similar. And so I ended up moving to MEMS, which had all the things that I had found interesting about my internship, but did not have any of the things that I found boring. And so that was like literally the summer before I applied to grad school, I decided to change up what I was going to be focusing on. Undergraduate research. So this is a big one. Professors usually love the free help, and it's a way for you to get experience without, without having to apply to a job and all that stuff because, you know, jobs are competitive. In fact, there are several ways to actually get paid to do undergraduate research. A lot of campuses have programs for summer research where you can get paid. One such program that's funded by the federal government is the NSFRU program, where you can apply and then they'll place you in a school and you can actually go to another school over the summer and perform research there, and you actually get like you get paid for that work. So it's nice where you can see the country, you can experience some research, and then you also make some money. And then there's some colleges, some campuses have programs for community college students to actually perform paid research at a university during summer. For instance, like my lab, we're part of this. We're part of this program at UCLA, and it's called the Santa Monica College UCLA Science Research Initiative, where students at the Santa Monica Community College can go to UCLA for the summer and see what it's like to perform engineering research. And so, like, you know, helps them inform on what they want to major in, stuff like that. So really helpful. Take electives and see what might interest you. That's just kind of logical. Like, you know, if something might interest you, you should learn more about it. Taking a class, I understand, is a big commitment because classes have homework. So if you aren't sure you want to commit to a class, I recommend like just going to the library and see if you can grab the textbook for that class and then seeing if that interests you. because then, every bit of information helps you make a decision. Professors usually love talking about their research. And so if you email a professor saying, can we talk about, like, I'm interested in what you're doing. Could we talk? I want to learn more about it. They'll often be willing to meet with you during their office hours or something like that, just to chit chat. If you don't know any people that might be interested, that are interested in that, you can talk to your academic advisor who will put you in contact. That's actually, when I was interested in MEMS, I did not know a single faculty member at my undergrad that did that. And so I contacted my faculty advisor, and he actually set me up with an appointment with a faculty member that did MEMS research. And we talked for like an hour or two. He kind of told me everything I wanted to know. And like, obviously I liked what he said, because that's what I got my PhD in. One important thing is, don't be afraid to try new things. When you are an undergrad community college student, you're going to have a bunch of different experiences, different internships, different classes, all that stuff. Don't pigeonhole yourself into something so early. You don't need to do, like, if you do research as an undergrad or community college student, you don't need to do your PhD in that field. If you have your internship in a certain field or a job in the field, you don't need to do your PhD in that field. And then if you can't manage to like if you can't figure out exactly what you want to do your PhD in, or if you don't even have the, your dream department didn't pick you up, or your dream your dream advisor wasn't interested in picking you up, or he had no funding. Don't stress, because your career probably won't be what your PhD is actually in. What matters more for like your long-term career is the skill sets you learn during your PhD. And so everyone knows that good grades if you're going to go to grad school, at least do what you can. But one thing that people don't think about is letters of recommendation. Typically you'll need like 2 to 3 when you're applying. Naturally, you think you'd get a good letter of recommendation if you do well in a class, but a professor can't write a good recommendation letter if they don't know who you are. And so a lot of times, like, if you're doing well in the class, you don't go to office hours or whatnot, you don't really participate because you don't need to ask questions because you understand everything. But now the professor doesn't know your name, doesn't know your face. And so when you ask for a letter of recommendation, they're like, who are you? So if you are understanding things well, after class or something, you can always ask just like kind of more advanced questions. Because again, professors, like, in my experience, professors and TAs, because I was a TA, they usually love it when students are really engaged and they're actually really interested in the course material. So asking advanced questions like, oh, like, what can this be applied to? Do people actually like do this? Like, if you learn like a certain, if you learn a certain, like, let's say you're taking a manufacturing class and you say like, you learn about a certain manufacturing technique, like you can ask, like, do people actually do it the way you taught us in industry, or is this just like a really simplified way? Do they have to worry about errors, tolerance, that kind of stuff? And participate class discussions. Other places you can get letters from, obviously, professors you've done research for, or managers you've done internships or jobs for. That's because letters of recommendation, they, at least in my experience, can carry a lot of weight with potential advisors. Because they're a way for people to vouch for your skill set. Like, are you really, because again, it's a PhD is essentially a job. And so are you really prepared to do the work? And one thing I think is important to consider is why you're applying for a PhD. And there's tons of good reasons. They're all equally valid. Maybe you just like the idea of doing research. Maybe you think being a doctor is really prestigious. Maybe you don't care about any of that. You just have an idea of what kind of career you want, and a PhD will help you get there. Maybe you just want to learn. Like, it's still school. You're still learning a lot. Again, they're all valid. But I personally think, and there's only really one reason not to pursue a PhD, and that is because you feel like you're supposed to, or you should. PhD is a big personal commitment, and if you're going to commit years of your life to something, I think it should at least be for some kind of concrete reason. I mean, it could be for a free T-shirt or whatever, as long as it's a concrete reason. Because if you just do it because you feel like you should or you're supposed to, I will say there are plenty of ways to be happy and successful without a PhD. That being said, if you're unsure if your PhD is for you and you get into a program, you can always start the program and leave it. So if you're on the fence, that's an option I think a lot of people just don't realize they can always consider. And so now that we've gone over kind of what I really wanted to say about what you should know about being a PhD student, I wanted to move on to just the meat of the talk and like talk about just what are MEMS. And so before I define what MEMS are, I want to define what a transducer is. And a transducer is a device that is actuated by power from one system and supplies power usually in another form to a second system. And this is really just a fancy way of saying a transducer is something that allows two things to interact. In practice, one of those things will be yourself. Transducers broadly fall into two categories: sensors, which let you measure things you normally can't by converting a signal that you can't measure into something you can measure, like a voltage. That's very common. And then there are actuators, which converts a signal you can apply, probably again, some kind of voltage or electrical signal, to something that can like change your surroundings. A simple example of a sensor is just a microphone, takes sound waves in the air and converts it to some kind of voltage output you can now measure. A laser is an example of an actuator. You apply some electrical power to it, and then now it is converting that energy into light energy. And an antenna is kind of a special case because if you're using it to receive signals or transmit signals, it can be either a sensor or an actuator. So you can see the boundaries are very fuzzy. And so what are MEMS? MEMS stands for micro-electromechanical systems, and they're basically just micro-scale transducers. These transducers are mechanical devices that interface with electronics, converting mechanical signals to electrical or vice versa. And so the reason we like electrical is because, you know, electronics are just very easy to, like, it's just a very easy way to control things. We have basically ever since the computer's been invented, it's been very easy to control things using electrical signals. Now, how small is microscale? 1 micrometer or 1 micron is exactly 1/1000th of a millimeter, or 1/millionth of a meter, which is, to calibrate you on something you can actually probably hold, is roughly 1/100th of the thickness of or the width of a human hair. Depends how thick your hair is, but about 1/100 the width of your hair. And so the image on the right is an example of MEMS resonator, which is just a resonator is just a device that's meant to vibrate very strongly at one frequency. The scale bar at the bottom, that white bar here, is 200 micron. And so basically almost everything you see in this image can be fit in the space of maybe like 3 hairs, just side to side. That's how small these structures can be. And so what's the point of making them so small? Small devices take up less space, which makes them easier to combine with circuits, because, you know, transistors and whatnot, they're all really small. So if you're able to put them all together, the less wiring, the less hassle. It can lower costs, it can lower signal noise. They're making these sensors smaller, getting them more tightly integrated with circuits is just often very beneficial. And then, so if they're smaller, you can actually fit more sensors on a single chip. And so this lets you do something called sensor fusion, which lets you combine different signals from different sensors to get measurements that are like much more accurate than you would if you'd use any of them individually. And honestly, it's just kind of cool. Like, you know, I make things that I can't see, but if I put on a microscope, I can confirm that they're there. And I know that they're only like a few hairs wide. And I just think that's intrinsically very cool. How do you make them so small? Basically, MEMS borrows a lot of manufacturing techniques from the same way they make transistors, which are kind of the foundational building block of integrated circuits, which are these basically which are the building blocks of essentially all electronics. If you ever cracked anything open and it has like a green PCB with a bunch of black squares on it. Each of those black squares is an integrated circuit, probably filled with thousands of little miniature components in them. And so they're made that small by using light to do the patterning. So light wavelengths are usually, that are used for these, are usually have wavelengths of about hundreds of nanometer. And so you can make things that are a few times larger than the wavelength. So that's micro scale. 10,000 nanometers is 1 micron. And so about 10 wavelengths if you're using something that's like 100 nanometer light. And there's a lot of manufacturing techniques that have been developed just to make these MEMS devices, because they are often a lot less straightforward to make than transistors. So a lot of research has been done on making manufacturing methods for just MEMS devices. It's so important actually that research in microscale manufacturing and anything that is just uses microscale manufacturing is often also called MEMS when you go to these MEMS conferences and all that. So yeah, manufacturing research is a big aspect of MEMS research. And so there are a ton of applications. Honestly, it would be impossible to fit them all in one slide or even one presentation. But I wanted to draw attention to a few, like 4 that came to mind. One is an inertial measurement unit, also called an IMU. These things measure rotation, acceleration. These essentially are the tilt sensors in your phone. They are used in like VR headsets to help track how they're moving. They're actually also used in your car. If you have, oh, it's been a while. So yeah, if you have like a newer car, like maybe not something from the 80s, but they are used for like the airbag sensors. They, not IMUs, but they use MEMS pressure sensors to check your tire pressure, stuff like that. A lot of the safety features in your car actually uses MEMS accelerometers and gyroscopes to kind of make sure you're not spinning out of control and stuff like that. One application you might not know about is actually printer inkjets. These MEMS devices are actually used to precisely squeeze like the hyper accurate amounts of the ink you need while printing. Many projectors use these micromirror MEMS devices developed by Texas Instruments, which is the same Texas Instruments that made those calculators, those graphing calculators. Each of these micromirrors will rotate, and by doing that, they can control kind of how reflective each pixel is in these projectors. They're super popular. They're in so many. One of the biggest success stories of MEMS companies actually is this company called SciTime. And what they did is they actually were able to make MEMS-based clocks that were a fraction of the size of traditional timing circuits. And so shown here for scale is kind of a traditional quartz timing reference, 1.6 millimeters by 1 millimeter. The MEMS one is just shy of 0.5 millimeter square, much, much smaller. And so I believe they've been adopted in like almost all the Apple products. SciTime's had a lot of success with these MEMS resonators. And again, this is all just a small fraction of the applications that are used. With all the electronics that are kind of everywhere today, MEMS devices are also everywhere with them. And so I just want to go over like kind of 2 broad types of MEMS devices. There are a ton of different types of MEMS, because as you can imagine, like transducers is a very broad field. I'm only going to focus on 2. The first is going to be what is most, without a doubt, the most popular, and that's the electrostatic MEMS device. All you need, if you've ever done like laundry and like the clothes have been stuck together, like you got a sock stuck on a sweater, you basically already understand how an electrostatic MEMS device works. All you need is 2 conducting plates, and you hold one fixed and you attach a spring to the other. And when you charge these plates, because of the static electricity, they want to come together. And so there's a force, which will make, like, one of these plates are held fixed. So the one with the spring will now move. And once it moves, if you remove the charge, it will spring back because there's no more force pulling them together. And so this can also be run in reverse. And so you can measure how the charge changes if the plate is moving. And then that's kind of how these motion sensors work for MEMS, is they have a plate, it's going to move when the whole device moves. And so they can actually measure how that the charge changes because of that motion by running this in reverse. And so these types of MEMS are really popular with the IMUs, which I just discussed, clocks, and actually MEMS microphones. A lot of the microphones in your smartphones and stuff like that, they're actually also MEMS devices. And so shown here is an example device. It's the same device from a few slides ago. This is an electrostatic MEMS device. And then you can see all the pairs of conducting plates they have, just here highlighted in red. And so these are electrostatic MEMS. This is my bread and butter. Piezoelectric devices are the basis of my PhD. To grossly simplify, oversimplify, a piezoelectric material is a material where you deform it. So you can like squeeze it, stretch it, whatever, and it will generate the charge by itself. You don't need to put a charge on the piezo. And so now there's a charge generated, an electric field is generated, and you can now measure that electric field to do a lot of different types of devices. Probably one of the, yeah, so there's a lot of different applications. The printer inkjets that I discussed like 2 slides ago, they use piezoelectrics to do the squeezing. Like you can run this reverse. You apply voltage and it precisely squeezes out the right amount of ink by compressing. Timing, quartz, if you've ever had a watch that said quartz on it, like a wristwatch, that's because that watch is using a piezoelectric crystal as its timing reference. It's vibrating at a very specific frequency, and then that frequency is going to be related to like a certain number of seconds or something like that. And then the biggest application that I think is like the most commercially successful application that I know of is RF filtering. So in your phone, you're simultaneously receiving all these different kinds of signals: Wi-Fi, Bluetooth, the regular cell phone signals, GPS, and all these piezoelectric MEMS devices are actually used to filter out these signals from each other so that you don't get interference. Like your Wi-Fi signal doesn't affect your Bluetooth, your GPS can still work while you're taking a phone call, stuff like that. My personal favorite application is shown here on the right. These are ultrasound transducers. By vibrating the piezoelectric membranes, which are these circles, and you can see like a simulation of one here. By vibrating these membranes like that, you can send out sound waves into the air, and by measuring the reflected sound back, kind of like echolocation, like a bat would do, you can do things like position tracking. If you're doing that periodically, you can see how everything is moving. In fact, I believe like Tesla, for their self-driving, they use ultrasound transducers to make sure, like, you know, the distances between the cars around them. You can also do things like imaging, like, you know, ultrasound is a popular technique for, that's how you investigate like a newborn in the womb. I've seen it applied for like fingerprint imaging, where you could just press it on a screen and then the ultrasound transducers will actually measure the ridges on your thumb and all that. Yeah, so my personal favorite, ultrasound. Again, MEMS is such a broad field. I don't think I could cover all the areas of research in a single presentation, but I just wanted to highlight a few interesting topics I haven't mentioned. The first is microfluidics. And so microfluidics is not MEMS per se, but remember how I said anything that uses MEMS manufacturing techniques tends to fall under the MEMS research umbrella. And microfluidics is like that because it uses MEMS manufacturing techniques to make microscale channels for fluids. And so these kind of devices are very popular for biomedical applications. There are optomechanics. These are devices that combine MEMS with photonics. And so photonics is essentially the field of like microscale light devices, like devices that use light. And by combining these like light waveguides, resonators, all that stuff. With MEMS, you now introduce a lot of ways to modulate the light, alter the light that you couldn't before when you're just using strictly optical devices. One thing that's pretty interesting is energy harvesting. And so these are devices that are made to kind of absorb ambient vibration. So like, everything's kind of shaking all the time. If the wind blows the tree will sway. And if you have an energy harvester on that tree, the idea is to use them to absorb some of that vibration and then use that to power electronics on a chip, like a small mobile chip, so that you don't need a battery to keep it charged. Because a lot of these things, like, if you want to, maybe you want like a chemical sensor or something out in the woods so you can check to see if there's a fire, like, it'll alert you if trees are on fire because a smoke alarm will go off. But then you don't want to constantly have to go out and change the batteries because, it costs money to pay people to do that. It's kind of wasteful because you need to buy the batteries and toss out the other ones. If you had one that was completely self-powered by an energy harvester, then you wouldn't need to change batteries until the device broke. And then I just mentioned this, but there's chemical sensing. And so basically you take a MEMS device and you treat the surface with a special coating that makes it sensitive to a certain chemical. And what will happen is that chemical will then, when the device is exposed to that chemical, the mechanical properties of the device will change. And by measuring those changes, you can now get an idea of what the chemical concentration is. And of course, this is just a really small sampling of all the cool stuff people are doing out in the MEMS field. And so now that we've discussed what MEMS is, I'm going to move on and kind of give a brief overview of my research on multiferroic MEMS. And I'm going to start with the motivation. And so first, consider your cell phone. Inside your phone, there's an antenna, which is the triangle looking thing on the right, the fork looking thing on the left, sorry. The antenna plugs into a filter, which then plugs into a computer that handles kind of all the data processing. The FCC tells the phone company, you can only use a specific frequency range. And the bandwidth, which is the size of this range, is really important because each frequency carries a signal. And the more frequencies you're allowed, the more data your phone can handle at once. But there's a catch because your phone has to transmit and receive at the same time. You have to be able to talk and listen at the same time. And so that these signals don't cross, what they do is they use half the bandwidth for transmitting and half the bandwidth for receiving. And they use the filters to kind of sort the frequencies. But this means that the total amount of data you can communicate with is now stuck at best to be half the upper limit from what the FCC will allow you to be able to do. But what if I told you you could swap out the filter for something called a circulator? Circulators use magnetic materials to kind of steer the direction of electromagnetic waves. And this means that anything the transmitter sends only goes to the antenna, but anything the antenna sends only goes to the receiver. So they're completely separate. There's no crosstalk. And so you now doubled your bandwidth. These devices are actually really widely used. You can buy them online if you wanted to. But there are actually about 30 of these filters in your phone. And so you would need to buy about 30 of these circulators. They actually won't be that expensive if you buy them in bulk. But there's a small catch. To make room for all these, you'll have to you have to make room. And specifically, you have to carry around about a solid puck in half a cup in volume. And like I said, the circulators are magnetic. So you're now carrying half a cup of magnets, which you probably don't want to keep near your phone or your wallet. And maybe your chest pocket's not a great idea if you're like a little older, you have a pacemaker. And so why are they so big? And the reason for this, how circulators work. I said that they use magnetic materials to steer electromagnetic waves, which means the device needs to be, on the order of a wavelength for it to really do anything. And with a wavelength at about 300,000 kilometers per second at 2 gigahertz, which is kind of, standard Wi-Fi frequencies and all that, that's about 15 centimeters, which means the smallest device you can practically make for it to have any effect is about 1 centimeter. It's not just for circulators though. Antennas have this problem. There's these things called frequency selective limiters, signal and noise enhancers. These devices all use magnetic materials and electromagnetic waves, and they're all very limited on how small they can be. And we're at a point where these devices, the size of these devices are just getting to be a major issue. If we go back to a circulator, shown here is kind of the electronics for a radar module. The CMOS and MMIC circuits, these are integrated circuits. They take up about the same space as a circulator, which is the magnetic component all the way on the left. But the CMOS and MMIC components are literally thousands of miniaturized components. The circulator is just one. And so you can see it dramatically takes up proportionally way more space. And so to miniaturize these, you can't use electromagnetic waves. The wavelength's too long. And so what we do is we use acoustic waves. And the reason why this approach is so attractive is like the speed of light is 300,000 kilometers per second, but the speed of sound in a material is about 3 kilometers per second. This means that the size reductions are about 5 orders of magnitude, and calibrate you how big of a change that is. That is going from the size of a football field down to the size of a small flea. So big change. And then there's actually a lot of prior work using miniature acoustic devices for these kind of RF applications. Because they traditionally can be made a lot smaller, and they actually often have much lower damping, so higher efficiencies. And so shown here is like a set of filters used in kind of old school CRT TVs as an example. That single chip in the red replaced everything else you see in this image. There are more cases just like that. I mentioned the 30 filters in your phone. Those are all actually mechanical resonators already. Vibrating quartz crystal resonators, like I mentioned before, have been kind of the de facto choice for timing for up until very recently, until these silicon resonators, electrostatic resonators started coming on the market. And so back in the 60s and 70s, there has been work on combining the magnetic devices that I talked about before with acoustic waves, but then the work kind of just stopped because of the manufacturing technology. And so now I'm going to the solution is what we call multiferroics, because those old devices were very difficult to make because they had to use there's the machining processes just weren't possible at the time. But now we have the capability to deposit high quality, what are called magnetostrictive materials. So shown here is kind of a magnetic material shown in purple. A magnetostrictive material is a kind of magnetic material where if I stretch it, the magnetic dipole will actually move around a little bit. And so you can change the magnetic properties just by straining it. And like I said before, piezoelectric is just a material where if you apply a voltage, it'll strain, or if you strain, it'll generate a voltage. And so by applying a voltage to piezoelectric and combining with the magnetostrictive material, we can now kind of, at small scales, control the magnetization. And so you can make these magnetic devices that we're talking about using acoustic waves by using the piezoelectrics to generate the acoustic waves. And so this is kind of the general overview of my work, or at least my subfield, multiferroic resonators. And so they're really attractive because they offer a really energy efficient way of doing all this kind of miniaturization. One topic that we looked into during my PhD was using this technology for antennas. Shown here is a magnetostrictive material again. If I apply a strain, the magnetization will change. And I can attach it to a piezoelectric to use a voltage to create the strain. And so I can run this in reverse. And if I can change the magnetization, or with an applied magnetic field that then strains the magnetostrictive material, which you can then measure that strain using the piezoelectric. And what you actually have is a micro scale antenna now. And so they're really useful for a lot of mobile applications. One that has particularly gained a lot of interest has actually been biomedical implants. A lot of people are doing research on personalized medicine, kind of putting sensors embedded into patients, so the doctors constantly are able to measure all necessary information about a patient and then give very customized diagnoses now that they have like all this personalized information. But the problem is you need to be able to communicate with these things. Antennas, like I mentioned before, can be fairly large. You don't want to embed things that are on the size of like a few centimeters into a person. But now if you can make a micro scale antenna, it's now a lot more feasible. And so to study this kind of this type of a device, in my lab, we actually made these multiferroic bars, which you can see a fabricated sample here on the left, on the right, and here's a little cartoon of a side view of it on the left. And so this green layer is our piezoelectric layer, which is aluminum nitride is the piezoelectric material we used. This purple layer is nickel, which is our magnetic layer. And so by applying a magnetic field, we can cause the nickel to vibrate, which causes the aluminum nitride to vibrate, and we can then measure that vibration, acting like a small scale antenna. And then shown here on the left is kind of a schematic of our testing setup for this experiment. We used something called a laser Doppler vibrometer, LDV for short, which actually shines a laser onto the vibrating sample. And because the sample is moving, the reflected light actually gets a Doppler shift, and the tool can actually measure these small frequency shifts due to that Doppler shift and be able to measure how much and how fast the micro devices vibrating, which is really nice because naturally you can't see, you can't record the vibration with your eye because it's so small. But this lets us be able to measure the motion without actually influencing the device at all. And so the device is, the device is placed in a vacuum chamber because since these devices are so small, the weight of air molecules actually can prevent them from moving appreciably. And so it's put in a vacuum chamber and all the air is evacuated out. And we use something called Helmholtz coils, which are basically just wound wires to generate a magnetic field to drive it. And so shown here on the right is kind of the measured displacement for several different voltages applied to the coil, which the voltage applied to the coil sets the magnetic field strength. And we can see that when we stimulate resonance, which is, again, these devices are resonators, they are set to vibrate very strongly at a specific frequency. And so if you apply the force at that frequency or a frequency that can at least stimulate that resonance, you get much higher increases in amplitude. And this is what you want to see in an antenna because now it becomes a lot more sensitive. And so we've done this and kind of validated that you can make these micro scale antennas using these multiferroic devices. And so another topic that was covered we studied during my PhD was damping of acoustic waves. And so I keep talking about we wanted to use acoustic waves and multiferroics to miniaturize all this magnetic devices. The problem is the physics is not really completely understood. We know that mechanical waves are damped by these magnetic materials, but it's not 100% understood how it happens. So what we did is we fabricated what's called a land mode device, and it's shown here the structure on the left. Essentially, on the left side we have an acoustic wave that is generated by a piezoelectric actuator, and then it travels to the right where it's measured by a piezoelectric sensor. But while it's traveling, it passes through a magnetic film, and this magnetic film will introduce damping. We know that damping is going to be dependent on the magnetic field, and so we apply a magnetic field and we can actually try to back out what is causing the damping by measuring those trends. Shown here on the right is actually one of the devices we made to do this experiment. This scale bar is 100 micron. So this device is about 3 hairs long, maybe 4. So much smaller than what would be achievable using kind of traditional techniques. And so this is just our measurement setup made in the lab. We have an electromagnet here with our device sitting in between it. And what we did is we used the electromagnet to control the magnetic field applied. And then we actually also rotated the device to control the angle of the field, because we had a hypothesis that the angle would actually matter quite a bit, which was kind of the unique thing about our measurement in this case. And so shown here is just the change in absorption. 0 means like there's been no change. As it gets more negative, that means there's been more acoustic wave damping. As it gets more positive, that means less. And what we found is, as we expected, as we changed the magnetic field, which is the x-axis, we did measure an increase in the amount of damping. But what was new that we found out was that as we changed the angle, we were actually able to measure the magnetic field where we got this damping point changed for each angle. And the trends actually match what we were expecting. And we think that this damping is actually coupling due to spin waves, which are a special kind of wave that only exist in magnetic material, which has not really been, the interaction has not really been thoroughly modeled yet. And so we believe that this is kind of a new phenomenon that hasn't really been looked at in the field. And so that kind of summarizes my research so far. And then to summarize my talk, when pursuing a PhD, try to get a feel for the lab culture before joining. Your research will largely be directed by the funding in your lab. Not that that's necessarily a bad thing. Usually advisors will get funding on what they're already good at. So if, again, your advisor is going to determine probably your entire PhD experience. So make sure you have an advisor you like, they work on stuff you're interested in, and then everything will usually fall into place. MEMS are transducers that are made with dimensions about 1/100th of the width of a human hair, and they're found in pretty much applications all over in society these days: cars, medical technology, mobile devices, and then multiferroic MEMS, which is my specific subspecialty, is kind of a route to miniaturize all these magnetic devices that have been used in telecommunications and RF technology. We've demonstrated that they can be used as microscale antennas, and the field still has work to fully understand the physics behind these devices, as we've demonstrated in our one of our more recent experiments. And so with that, I'd like to thank you all for listening to my talk, and I'd love any questions if you have them.
Dr. Tiwari, I appreciate the time you took out of your busy schedule to address members of our college community and audience that is present with us here today. And I absolutely enjoyed your outstanding presentation as it was really interesting and informative. If anyone has any questions or comments for Dr. Sidhant Tiwari, please put them in the chat box or unmute yourself. Thank you once again.
Yeah. I also want to say, if you guys have questions later, I'm sure, I'll just tell Mahak that she can give out my email address to anybody who wants it. So you guys can contact me.
You could put your email in the chat as well.
Oh yeah, that's a good idea. Yeah. Yeah. If you have any questions later about doing a PhD or anything like that, like I said, I was kind of like the first in my family, like at least in my household, to apply to graduate school and all that. So I know what it's like to not really have questions and not really have people to talk to. And so I would be like more than happy to answer any questions later. Or like, I've been working at UCLA long enough where I've kind of picked up some professor habits. So I also very much like talking about my research. So if you have any if you have any questions on that, I'd also be more than happy to answer.
I had a question. So how long did it take for your PhD?
Okay, so I was a bit of a special case because mine was longer than what was kind of traditional in my lab. I got my master's, I think just shy of 2 years, because I went straight without my. A lot of schools have what's called an MS-PhD program, where you can be admitted into the PhD program without a master's, and then you can earn it on the way. And basically what that means is your first 2 years, you're just taking a ton of classes, more than a PhD student, and you'll typically take longer. So it took me total 7 years, but 2 of those years was getting my master's. And then honestly, those 5 years for my PhD was just kind of long. It was more me wanting to see some of these projects to the end than me being held back from graduating. So yeah, 5 years, but that's long. 5 years after my master's, but that is long. Like normally you'll see people, including their masters, will do 5 to 6 total. So like I did 7.
Any more questions, guys? Oh, we have.
What do I do now? So I'm a postdoctoral scholar at UCLA, actually up until the end of this week. I start a new job next Monday. But I've been doing research in, I've had 2 different projects. One is on kind of relatively out of my field. It's still magnetics, which is why I got put on it, but it is kind of position tracking for 3D printers, because the idea is like you can improve the accuracy of a 3D printer if you can actually track where the print head is to make sure it's actually staying on position. And then that's an issue on, let's say you're a 3D printer on a Navy ship, for instance. The ship sways and rocks, and so the print head will vibrate, and it's kind of hard to do that to measure where it is versus where it should be, and to do that compensation. So I have one project where we're using magnetic field sensors to track position. And then the other project was, it's multiferroic antennas again, but this one is focused specifically on developing, instead of just doing like a proof of concept, this one is specific to developing one for biomedical implants. But I will be starting a new job, still a postdoctoral researcher, but this at a Sandia National Lab next week. And I don't exactly know what I'll be working on then. So, yeah. And thank you, Anton.
If no one else has any more questions, we will, let's include this event. Thank you so much, Dr. Tiwari, for presenting, and have a great evening, guys. Thank you.
All right, bye-bye.